Blommaert from SISSA, who's going to tell us about the q-Schwarzian and its gravitational dual. All yours, Andreas.
Okay, hello everyone, and yeah, thanks for coming, and of course for the opportunity to talk. It's always fun. So yeah, today I'm going to tell you a bit, mostly about work in progress with Thomas Mertes and Shunyu Yao. The title of the talk is the q-Schwarzian theory and its gravitational dual. Okay, let's start with some very general introduction, which is not going to be very long. So you'll know the SISSA model some constants that I didn't write. As many of you know, the low energy physics of SISSA is governed by the Schwarzian quantum mechanics, which has a holographic dual as the ADS2 JT delta gravity. And I think it's pretty fair to say that over the last 6 years or something, 7 years, that duality has learned us quite a lot of things about quantum gravity and ADS. I know one could argue it's become the favorite tool of the community to study black holes. Now, interestingly, there's another limit of the SISSA model, which is known as double-scale SISSA, where we take this parameter q finite. Well, confusingly, this q is not what people have always been calling q in SISSA, so someone thought it was a good joke to introduce another parameter q. So what used to be q is now p. So we take p very large when we take n large, so like a lot of fermions talking to each other. We keep this new q finite. So the reason why this is interesting is because the theory is exactly solvable in this limit, in the same way that one could say the Schwarzian is exactly solvable. It means that we know all amplitudes of what we believe are interesting operators analytically. So there are many nice questions to ask about it, but the one question I was quite interested in is whether this double-scale SISSA system then also maybe has some tractable bulk dual gravity description. Maybe it's too much to hope for, but I want to convince you today that the answer is yes. There is a somewhat simple bulk dual. One a priori reason, other than following your nose to pursue this, is that people have argued since a while for some type of duality between double-scale SISSA and quantum gravity in the cylinder space. It's gonna happen a few times. Okay, so to motivate this bulk dual of double-scale SISSA, I will introduce and study something that we call the q-Schwarzian theory. It's a deformation of the ordinary, quote-unquote, Schwarzian quantum mechanics path integral, so 1D quantum mechanical theory. It just depends on a complex parameter q. I'll give you the details later, don't worry. Now, depending on q, I'll argue that this q-Schwarzian has the following bulk dual 2D delta gravity descriptions. First of all, if q equals 1, we have our good old JT gravity. If q is smaller than 1 and real, it will be dual to a sine delta gravity, because it's a sine potential. I know, I thought it was probably wise to call it QJT if I'm going to call this q-Schwarzian. And then if q takes values on the unit circle, it will be dual to a singe delta gravity, which already had a name. People called it Liouville gravity, but also recently people decided to call it Vidas over minimal string. So those are all the same things. Furthermore, the q real is more than 1 q-Schwarzian. You can show is equivalent to the core diagram description of double-scale SISSA, which I'll say a little bit about, but not terribly much. I will introduce it when it's required.
So, can I ask?
Yeah.
So Q is on a unit circle. I don't understand. Is there discontinuity from Q equals 1?
Well, no, actually not, because both for Q approaching 1, both go to JT gravity. I didn't write Q in the potentials. I did some rescaling, but yeah, because this is an introductory slide, and I thought the font should be extremely simple, maybe too simple. But there is a Q in the potential, and you'll see that. Okay, so there are several reasons why these inequalities seem somewhat interesting to me at least. So for the double-scale SYK case, I'll argue that, or I'll show you in a minute, that the classical bolic has a black hole horizon and also a cosmological horizon. And there's a region where the classical solution of the metric is just ordinary DS2, let's say. By which I mean nothing more or less than the curve that R equals 2. And so it needs some type of potential for a DS2 holography from a microscopic model. Another reason why it's interesting, well, you might think it's interesting or like makes it very uninteresting, but in the gravitational dual, I'll find a bunch of confusing new elements, which are markedly different from how we think about ABS holography. And I know, for me that's a good sign, because I think there's probably something interesting to learn there that we don't understand yet about the gravitational pattern rule for theories that are not asymptotically ABS. The second reason is that the double-scale SYK is essentially by definition a UV completion of JT gravity. Okay, we can do semantics discussion about what I mean by UV completion, so I'll just define it here. I mean a spectrum that has a beginning and an end, and that has like finite thermodynamic quantities. For instance, if I take the partition function, like e to the minus beta h, then this will be finite for beta is 0, and like a theory where the spectrum grows. And typically, if you think about black holes, we always have exponential growth at large energies. Such theories are never a finite partition function when beta is 0. So if you want to think about black hole duals, they should immediately strike you as peculiar because of the lack of exponential growth. Anyway.
Sorry, is the bulk what it actually is E? Because if you don't have an asymptotic boundary anymore, how do you measure the energy?
In our case, there is asymptotic boundary. Or there is a boundary.
There is a boundary.
No.
Okay.
And then you can use the usual ABM stuff. Or see what multiplies beta in the challenge.
Sorry, the fact that the spectrum is cut off, does this mean that I cannot keep adding excitations to double scale SYK? Like at some point there's a maximum energy state? Why does it cut off? There's a maximum energy state?
Yes.
Okay.
This is also true in ordinary SYK. Okay,
Because it's not apparent from the bulk, that's the issue, right?
Yeah, it's not apparent from the bulk.
And you mean at finite end?
I think I'm probably here in lines. This is double scaling limit, right? So I take b to infinity and n to infinity in this correlated way.
So is the idea that you, for example, you keep Q a little bit less than 1 or something, and that's the place where this happens?
Yeah, indeed, Q a little bit less than 1 seems to be a very good regime where, there's semi-classical control. In SYK literature, people call this large Q SYK. This Q is a little bit less than 1.
And can you remind us what the right edge, how the right edge scales with the SYK double scale SYK parameter is? Like what the maximum energy is as a function of N and Q and or P. So are you saying that that's non-scale with N?
Okay. So So in the conventions that I will use, I have the following formula for energy. Energy is cosine of theta, where theta is the angular parameter ranging from 0 to pi. Divided by something like log q squared. Okay, I'm making this up as I go because I don't know the answer. So the question is, what is the maximum value of the energy? Yeah, it's order 1 over log q squared. Okay, so 2 over log q squared if I put the 0 at the origin. Okay. Yeah, and finally I'll spend a good amount of the talk talking about this Liouville gravity case. The main motivation for me, well, you could argue it's a fun theory to look at anyway, which I think is true, but the main motivation for me is that it shares a subset of the confusing new elements with the double scale SYK case, but some of them it does not. And I think it's always good if you can isolate a subset of the problem, solve them first, and then tackle the more complicated case. So it'll be sort of a testing ground. And interesting if it's alright. Okay, so the remainder of the talk, this is somewhat the setup. These first 4 things will be knocked out very soon. I think, 2 weeks is the idea. But okay, you know how these things go. The last quarter of the talk will be much more work in progress and therefore less understood, but maybe also a little bit more interesting. Okay, I'll start with some basic stuff about dilaton gravity. And actually I will keep most of the talk pretty basic and try to talk only about classical solutions and their comparison, although we have good quantum evidence for the dualities and so on. So I'll start with dilaton gravity and I'll just discuss their solutions basically. So by dilaton gravity I mean the following action. So delta times r plus some potential and then some boundary terms. Classical solutions well known and relatively easy to derive from this form. Like it's very simple to see. I mean, most of you probably know if I look at a metric like this that r, that square g r will be like f double prime. And now if I take the phi variation of this, I get like r equals v prime. So it gives like f is integral of v. Very easy to solve. And now the first thing I want to do is just compute the on-shot action on this guy. But I want to do it in a scenario where I keep the area fixed, and the temperature fixed, and I vary them independently. It's known how to do that. It's like what people do with fixed area states, though I forgot the references here, for which I apologize. So what happens is in these cases you have a conical deficit at the horizon. It's like if you take Riddler space and you put it at the wrong temperature, then it's just a cone. And the conical deficit you can just compute from Gauss basically how strong it has to be when I have a mismatch. The reason I'm taking this tangent is because it's important to include the singular piece in square GR to get the correct on-shot action. So in the end it looks like this. So this guy you should view as the energy, and this guy is the area. So the equation is of this sort. And this is universal for any type of dilaton gravity. But now we'll specialize to the cases that we're interested in. So now Arvin, here's the log Q's, which will make the Q dependence, which makes life a bit easier. Here if I take the log Q to 0, or Q close to 1, this just becomes 2 phi, which is JT. And the other theory will be the same. So if you write down the metric for this, I'll have a picture on the next slide. It looks like this, and the point is that it is 2 places where the metric vanishes. One is like the place where the dilaton is minimal, and the other is maximal. So one is the black hole horizon, and the other is a cosmological horizon. Yes.
Your goal is to fix the area and then integrate over energy. In other words, you don't want to fix the area at the end.
I don't want to fix the area at the end, but I just want, it's a bit academic, but I like the way of going the wrong way.
Okay.
I want to get the formula immediately in this shape without having to approach compulse transform. Okay, so what I wanted to take away is this answer and try to remember it for later in the talk, but I'll flash it again multiple times. So this is the classical thermodynamics from this potential. This mismatches notably with the double scale SYK. I think it's pretty easy to see this guy I can keep ramping up forever basically, so it will never, the entropy will not go down. So we'll see how that gets cured at the end of the talk. So a bit more details about this metric. The curvature you compute from it looks like this. It's just a cosine, and here I made a plot for those of you who like myself. It's a nice mix of cosines and sines. There's two interesting regimes. One is like okay, so this thick line is a black hole horizon. The dotted line is a cosmological horizon, and depending on how I do my energies, I can switch the horizons from left to right. So if I go to very low energies, my horizon is here, and like the near horizon region will be JT gravity, ordinary ADS2 JT gravity. Another seemingly interesting regime is if I two parameters, so that my horizon is here, and then essentially I have a constant curvature spacetime, but the one that would correspond to a DS2 point of gravity. And then behind the horizon there would be like a initially exponential expansion, then the expansion slows down and actually turns around. It somehow seems to make sense to me if you think of finite Hilbert spaces, but that is a very big comment, so I'll leave it at that. One weird thing is that there's no asymptotic AUS regime or asymptotic regime of any sort, so one can wonder where the holographic boundary is. And I should say I don't 100% understand that, but we'll return to that later.
Sorry, here you mean that the space is ds for part of the space-time?
Yes.
Asymptotically, it's not yet.
Yeah, whatever you mean with asymptotically, but yes.
Well, in the previous slide, phi ranged from phi h to infinity, right? Maybe even the previous slide, right? You were integrating via phi from phi h to infinity.
Yeah.
And your cosmological constant depends on cosine phi, right?
Right.
So essentially, is it correct to imagine that your solution is ds for that choice of q? It's ds close to the horizon, then it becomes ADS, and then becomes ds again, and ADS.
Yeah,
and
something
the cosine, so it keeps oscillating.
Something like that, yes.
Okay.
And yeah, it's not super clear to me where this asymptotic boundary is, because I write infinity here, but infinity is not a good asymptotic region of this metric because it just keeps oscillating. So it's no place where you would do like a counterterm subtraction. I think it's maybe more like phi to I infinity where this metric does blow up, and there you can have like a blowing up piece that you can subtract as a counter term and a finite energy term remaining. But yeah, the global, how to view that really in terms of cosmological space and etc. I'm not. I should say I haven't thought enough about, but that's something I still want to find out eventually.
Actually, can you say something about how this description of DSSYK is related to the chord diagram stuff?
Yes, I will say that later. But that will be more toward the end of the talk about for sure. For now, I just want to keep it on a little bit. Okay, I can say one word about it. Namely that for me the chord diagrams I think is strong evidence that it's a target space description. if you want, in the same sense that, say I have the example I think we best know is the 3D Chern-Simons theory in living in the bulk. But let's take a group for the Chern-Simons theory that is like 18-dimensional or something. It's dual to a Westerminer-Witten model, so a 2D CFT, which has a description as string theory in an 18-dimensional target space. I think the chords in this language are the target space, and this theory is like the analogous to the Chern-Simons. This is the case where you have actually a path integral over metrics, etc. The boundary theory I will discuss, the q-Schwarzian, is a quantum mechanics of a particle on a target space. Ordinarily, quantum mechanics does not imply quantum gravity in the target space, unlike strings. So I don't think the chords have actually a gravitational path integral sitting there. That would be my current statement. Okay. Yeah, very quickly, let me also flash the delta gravity solutions for Liouville gravity. So they look like this. So here B is a parameter I take small, and it parameterizes this Q on the unit circle. And the metric looks like this, thermodynamics looks like this. Basically, a cosine becomes a cosh. That's what you need to remember. And the curvature just keeps on growing and growing and growing. Now, one thing that's nice about this Liouville gravity is that people have solved it exactly using CFT techniques a long time ago, basically, but then maybe with more gravitational language recently. And if you quantize the q-Schwarzian that I'll introduce, you can actually recover precisely those amplitudes. Which is a way of proving that these theories are quantum mechanically dual. But okay, at this point I have not even yet introduced the q-Schwarzian to you, so it's probably about time that we get to that. Okay, so here's the thing I will refer to as a q-Schwarzian. It's a six-dimensional phase-space path integral. So people of you who, well, mostly probably at some point have come into, have heard about the Schwarzian theory, and usually you think about it as a theory with the action that is literally a Schwarzian derivative of some field F. But there's there's equivalent ways of writing this theory namely as a phase-space path integral, instead of this being more like the whatever typical Lagrangian form. And the phase-space version of this guy is a four-dimensional theory where you have basically a field phi, beta, p beta, and some Hamiltonian. This is 6Z, which might confuse you, but there's actually yet one constraint that we have to impose. And you can convince yourself that if I take log Q small, that this becomes the ordinary Schwarzian theory that we know. So one thing I want to say about it is that perhaps surprisingly, this system has a bunch of conserved currents which span two copies of an algebra. And when we quantize, the algebra becomes the algebra of a quantum group. Quantum groups may sound scary, but that's because math people use way too many definitions. And actually, it's super easy to explain in layman terms. I'll say a few words about it. Okay, just to summarize, I'm going to repeat this a bunch of times, so hopefully you remember that I claim the following set of dualities. And let's summarize which evidence we find for these dualities. So first of all, I'll be able to show that the Zelton gravity is just equal to the q-Schwarzian path integral by going to a first order formulation that is a topological gauge theory and a generalization of 2PBF. And afterwards I will match the classical solutions in both sides of the duality. And finally I will discuss let's say mismatches of both the q-Schwarzian and the Dalton gravity with Donald scale SYK and how to resolve them.
So this dilaton gravity is at the level of the disk.
Yes.
Question. Maybe this is obvious, but for the Liouville gravity case, what does it mean when you take Q imaginary? In terms of the original SYK?
Probably no relation to SYK. Not an obvious one at least. So that theory is like motivated by itself, because people say that mostly from a bulk point of view, CFT style. Yeah, I don't think it's obviously related with SYK. Even the word analytic continuation is somewhat at least a suspect here. It works on the level of the action, but the quantum amplitudes already look very different, and the thermodynamics is very different. But first, before we go into the classical solutions and the proof, I want to give you a small taste of how the quantization works. So this is a couple slides which are not essential to follow. I'm just going to go through it pretty quickly. But as I said, there's a there are 6 classical currents. And when you quantize, they satisfy the quantum group algebra. You can show also that the Hamiltonian of our theory becomes the Casimir of a quantum group. So now let me tell you what a quantum group is. An ordinary Lie group, we can always decompose, well, basically by exponentiating generators. And the prefactors of the generators are the coordinates of the group manifold, if you want. So what changes for a quantum group is that the generators, instead of having a linear algebra, have a nonlinear algebra. As you see, this is nonlinear. And for the coordinates, this also implements that the coordinates on the group manifold become non-commutative. Which again sounds pretty awful, but it's not so hard to deal with actually when you start with calculations. So the takeaway is that the q-Schwarzian is quantum mechanics on a quantum group. And the quantum group, the non-commutative manifold is the target space on which the particle propagates. And this is the language in which the chord diagrams appear. Yeah, people have, I think, written recently a good amount of papers about seeing how quantum group symmetries act on chord diagrams, etc. Now, this identification as quantum mechanics on a quantum group is useful because it means that the wave functions of the system are representation matrices of the quantum group, which are also again not too tough to compute. Long story short, the wave functions you find match with wave functions that people found via chord diagram techniques. Maybe one thing I want to emphasize is that there's this somewhat known formula for a transfer matrix in double-scale SYK. This is extremely easy to get out of the action we wrote down. It's just like literally the Schrödinger equation for the quantum for the theory. You just do canonical quantization.
Sorry. Quick question. When you take Q to 1, you should get the Schwarzian result.
Yeah.
But there, the wave functions are not the SL2R, as far as I know. They're not the SL2R group elements.
There are the Bessel functions are representation matrix elements.
Just of SL2R or
Yes.
of SL2R plus? Or
SL2R plus probably, or
so does the plus come out somehow here?
clear. If you take the limit from the Liouville sides, that does come out. Like in Liouville gravity, this plus makes an appearance. So from that point of view, it's very natural. From this, I don't know, or I don't understand. Okay, so that was a taste of quantization. One point worth mentioning is that the coordinates on the group manifold, which are ordinary fields in our pattern integral, when you quantize, they become non-commutative, and when you compute wave functions, they become somewhat discretized, in the sense that if I compute inner products of my wave functions, the integral, let's say, that you usually do to compute overlaps gets replaced by a sum. So it only samples the wave function at certain points, which is quite peculiar. It doesn't happen for the Liouville gravity case, which is based on a subtly different quantum group. The value of Q is very relevant in this case. Okay, now let me give you a quick proof why Dalton gravity is exactly equal to the q-Schwarzian. If you're not interested in this, again, you can skip this and you can tune in a couple of slides where I discuss the classical solutions. So I'm going to start with this action here, which is the Dalton gravity in field line formulation. It's a bit long, but this guy is a potential. If you remember, VF5 is a sign. I may have gotten some sign wrongs here, but forgive me for that. And then we have some boundary terms that come with it. And this guy you should view as like a counter term. Now I'll introduce some notation. Don't think of this as actual Poisson brackets, it's just a notation. And with this notation and a good filter definition, this guy becomes what people have called the Poisson sigma model. Looking like this. So here's basically a PQ dot term if you want. And here's some funny term that we'll soon discuss, and then on the boundary there's a Hamiltonian term. And now what to do with this funny term? One comment is that this is just a non-abelian, it's a generalization of 2D BF theory away from Lie groups to quantum groups. Which is, and the point being that this JA, JB can be nonlinear in these quote-unquote currents H, X1 and X0. If it were linear, then it was BF theory, but because it's not linear, it's something else, which we would call Poisson sigma models. So what we make of this term is that this field eta only appears here, so we can view it as a Lagrange multiplier that constrains this brown guy to vanish. And we can use that to solve the theory in the sense that for theories with constraints, you can do two things. Namely, either you can quantize the full theory and then impose constraints in your Hilbert space and model by null states. But often in physics, it's much easier to go the other way around and to first impose constraints on the data on a Cauchy slice, and then quantize at that point, mod out by gauge transformations, which are generated by the constraints, and then quantize the resulting much smaller phase space. And that is the way that we'll be able to show that this guy is identical to the q-Schwarzian, namely the resulting classical phase space with the Poisson brackets and Hamiltonian will be the same as that of the q-Schwarzian, making the theories manifestly identical. And it's the same way it actually works for BF theory. Just this case is less studied and was less much the previous.
So, Andreas, can you tell us what is the analog of gauge transformation? Just to see, like, to get some intuition about why this is like a gauge theory for a quantum group?
Yeah, it's a bit hard. I know a super precise answer to that. There's two things I can say. So one is that it is a system with like very non-trivial constraints, and constraints come with gauge freedom if you want. If I impose constraints, there is going to be a redundancy that I have to mod out by. That is one comment. Now what else did I want to say?
Maybe I'm just a bit confused even about the notation. Here A is the analog of the gauge field.
Yes.
I see. So somehow when Q is equal to 1, this just becomes trace JF or something like that after you integrate by parts? Or
Yes.
okay.
Yeah, I think in going through the solution, it becomes clear that a lot of data about A is actually irrelevant. That I don't have like a super sharp statement as saying, I can do A to A plus D5, and then obviously there's nothing. But there is it is clear that a large set of configurations of A are completely equivalent to one another. I just don't have like this a very short equation for it as you would ordinarily have for the HGs. Maybe some of that will become clear when we go to the solution. So something that was known about this is that the classical phase space which you get after imposing this constraint and mulling out by redundancies is actually 6D, which if you think about it is a huge simplification, because you start with like 6 fields worth of degrees of freedom and you go to just 6 numbers worth of degrees of freedom basically. So it's an enormous reduction. If you want going from like the 6 fields will have to be specialized everywhere on the Cauchy slice. So you usually have six functions fi of r, and we go to just 6 variables fi basically. So a lot of things are removed. So what I want to present to you now is a quick way to construct this classical phase space. So for that, you have to choose a functional or a function g that depends on this current j, and it can be any function. This is, if you want, part of the k3-dimensional system, it turns out. Then someone at hoc I'll tell you to choose 6 values for fields xa, which I have not defined yet, but still I want you to choose values for it. This fields will depend on the radial coordinate, and the radial coordinate is the one that parameterizes the Cauchy slice. So remember that I want to solve constraints on the Cauchy slice. And you should think of these as setting something like initial conditions at the boundary of the Cauchy slice, and then we will basically, given those initial conditions, determine the full field on the whole thing. That will be somewhat how the holography works. So I'm asking you to choose these 6 variables and then think of functions xa of r, ja of r, and then I'm telling you to define functions ba of r as particular combinations of xa and jb. And I'm choosing the combinations that I want you to choose. Namely, there's a relation P in terms of x and j that I get from the q-Schwarzian, and I'm just telling you to pick that because it will help me solve the system. At this point, it's just arbitrary choice.
So if the cube goes to one limit, the phase space is just 2-dimensional, right?
It's actually still 6-dimensional. So this may be a confusing point. The Schwarzian has a 4-dimensional phase space. One way to see it is the Schwarzian derivative has a term like f double prime over f prime squared. Because of the double prime, you need 4 variables instead of 2.
But in terms of the JT gravity description, isn't the area or the mass like all that to specify and so on?
Yes, so there's 2. Okay, I wasn't going to say it, but I can say it now. So there's roughly 3 ways to think about this theory. One is the 6D phase space. The 2 is a 4D phase space, and it's analogous to the ordinary Schwarzian, and you should think of it as describing a gravitational theory with one boundary. The reduction from 60 to 40 comes because the boundary comes with the boundary condition. A boundary condition is one constraint, and there's one constraint, then there's also one degrees of freedom that become redundant, roughly speaking, the conjugate of the constraint. Then there's a third case which has only a 2D phase space, and that applies to a system with two boundaries. So if you think, for instance, of just time evolving the eternal field double, for instance, and that is maybe the picture that most of you are more familiar with. In this case, I have boundary conditions on both ends, which takes another 2 away from this guy. At this point, I'm discussing this guy without any constraints, but it's not art after effects to which it is constraints. Is that help?
Yeah, but I'm still confused because I thought the Schwarzian describes the dynamics of the boundary itself. Isn't that correct?
Yes. So the 4D phase space, if you take the ADS2 disk, it has 2 coordinates, right? We can call the coordinates z and theta. So the 4D phase space would be z theta, the conjugate to z and the conjugate to theta, describing the position of the quantum particle on the surface.
But then what's the angle of the 60?
Well, the 6 doesn't have a direct analog.
I see.
It's okay. The 6 is like, if you want, you can view this as a quantum mechanics on ADS3 with a constraint. ADS3 being SL2R. So if you want, this would be like a quantum mechanics on non-commutative ADS3. This is quantum mechanics on non-commutative ADS2. This is something fun. Okay, so to solve the system, I will somewhat ad hoc consider classical mechanics radial evolution that's generated by this function G that I chose, which I think of as some sort of Hamiltonian. And now the point is that if I claim that the solution to the constraint is obtained by writing out the gauge field as follows in terms of the solution of the classical mechanics. So I just solved this guy, I got some functions xa and ba and ja, function of the initial conditions that I chose. I can write my gauge field A in terms of these solutions. And it's pretty easy to see that that solves the system because I can invert this equation and write it as such. And now you can see that if I take A to be like the derivative of this quote-unquote Hamiltonian, then these are just the Hamilton equations of this classical mechanics. So as such, I've solved my constraints, and I found the 60 phase space, which are the initial conditions of these variables. Now, I can compute the Poisson brackets on this thing there, that's surprisingly standard answer. Other than that, I had the Hamiltonian term sitting right there in the boundary action. So that sort of, completes the derivation that this Poisson sigma model is completely equal to a simple quantum mechanical system. And in fact, this works for any, you can do this game for any dilaton potential. So I'm telling you, there's a known holographic dual for any dilaton gravity theory, but we're interested in a specific case. Okay. I'm going to skip this slide. Just a summary of what we've done. So we've taken dilaton gravity, went through gauge theory, and showed that it's equivalent to quantum mechanics on a quantum group, or more generally a quantum mechanics system. If I then impose a constraint that puts boundary conditions, I get q-Schwarzian quantum mechanics. Now I want to discuss its classical solutions and compare to what we had before. Okay, so remember this action. I'm just going to do some filter definitions, rescaling a bit. So the reason why that's useful is because now I get like a huge parameter in front if I take q to be close to 1. So q close to 1 in this language was b close to 0. Now the theory behaves classically, and I should be able to trust the saddle point. So quite surprisingly to me, the theory doesn't look very simple, but you can still find analytic solutions after a bit of work. And in fact, in terms of the field phi, they look very simple. This answer in particular, what I'm telling you that you should compare it to the bulk 2-point function that people computed in Liouville gravity. And in fact, you can show that this matches. But I'll show you the DSSYK case in a few slides, which may be more familiar. But yeah, let's briefly discuss the thermodynamics. If I look at this solution that I have, you can see that one of the integration constants, alpha, determines the period of the solution. This is so annoying. Sorry, guys. Then the energy of the solution you can compute by just evaluating Hamiltonian, and for the entropy you compute like a volume of phase space. Putting this all together, this answer matches with the delta gravity calculation that I did earlier, which I think is kind of nice because, okay, there were still, the somewhat technical proof I gave the last 10 minutes. It is somewhat technical, so there's very simple computation here behind it that for me is strong confirmation. Okay, but now let's leave Liouville gravity behind us, and let's go to double scale SYK and what we know about that. So the way that people solve double scale SYK is via these co-diagrams, which I'm not going to say too much about. One thing I want you to know from this is that the number of chords is obviously a positive number. And the way this dictionary works is that the field phi, the q-Schwarzian, is proportional to the number of chords. Therefore, quantum mechanically, there's a constraint that phi has to be a positive number. Now, in the classical regime, where log q is much more than 1, you can take the exact partition function of double scale SYK and it looks a bit like this. Now, if you remember the gravity calculation for sine delta gravity I did at the beginning of the talk, you'll see that this is almost right, except that here I have this quadratic piece. And actually the quadratic piece is very important because it's a difference between the entropy going down or not. Namely, this formula for the entropy, so the entropy is the first piece here, it vanishes when theta is 0, but it also vanishes when theta equals pi. Whereas this guy just grows linearly in theta. So it's absolutely crucial to explain this from the gravitational point of view. Okay, I was puzzled about this for a very long time. But help came for me at least because we actually find exactly the same discrepancy when we first consider the q-Schwarzian bounding theory and not the block theory. So there's not anything wrong between the identification between the q-Schwarzian and the block. It's a problem that we have to solve in both cases. And it turned out to be simpler to solve it for the q-Schwarzian than learn what we do for the gravity system. So let's first discuss the q-Schwarzian resolution. Well, and the version of the problem also. Sorry, I have one more slide in between. Namely, people also computed the 2-point function in double scale SYK and its classical limits. The equation I want you to remember is this guy, which looks a lot like the formula I had for e to the minus 2 pi in the previous slide, except that the sign of theta was tinge of alpha. But that is, if you want, the standard analytic continuation between these two theories, where Q lives on the unit circle and it does not. So one thing that's also very funny about this is that this looks precisely like an ADS2 correlator, and I don't understand why, but we can come back to that later. Okay, so like I said, the solution of the q-Schwarzian system as just solving classical equations of this theory doesn't really depend fundamentally too much on Q. on the whether Q is on the unit circle or not. So there I can just take this added continuation since alpha to sine theta. And here I've added a somewhat at this point meaningless integration constant, which is just a shift of tau. But yeah, of course it'll have physical meaning, because I also added here. But at this point it's a silly integration constant that is absolutely none. I can compute the energy of the solution. It matches with both with double scale SYK and with the gravity answer. I can also look at the period of the solution, and it's 2 pi over sine of theta. And now this results in entropy, which goes linearly in theta. As we also found from the gravity calculation, but again, as I emphasized, crucial mismatches a lot with double scale SYK. Okay, so we have a lot of matches and a lot of mismatches. Okay, so can we get it to all match? So the resolution for the boundary theory is quite simple. Namely, we should still impose the constraint from the exact quantum theory that this field phi is positive, coming from the fact that the number of quarks is positive. From the boundary theory point of view, it's all ad hoc, but I mean, at this point, I'm the god of this theory. No, I can define it whichever way I want, such that it gives me the answers that I want. So I will define the q-Schwarzian theory to be a path integral over phi positive, because I'm only interested in the case that reproduces double scale SYK. I'm not interested in solving the most general quantum mechanics system in the world. So I'll take that as a constraint on my theory and see what it gives. Okay. For that, let's look back at our solution that we had. So it's this function here. I just plotted it. So it's positive for a while, and then it becomes negative for a while. So clearly, the negative piece I do not want. Unfortunately, in fact, this function is also periodic between its two zeros, well, obviously. So I can choose, in fact, to get rid of this whole region and just identify the function at this point with itself. So if I impose this constraint, I'm essentially choosing, if you want, a shorter period for the solution of my system than the one you would naively think. And the result of this, if you go through it and you compute entropy again, blah, 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 is that the classical period has become shorter. And now the thermodynamics does match with double scale SYK. So yeah, 2 comments about this. One is I already touched on that I've used as differential theory. The second is that this shorter period, yeah, people have attached a lot of weight to it. Also, like I said, it's crucial for the entropy to go down again. And there's a reason for the distinction between temperature and what people at Stanford have given many names, like a fake temperature or temperature, or you can choose your favorite. Now this fake guy, the naive temperature or system, it's relevant because it determines the characteristic time for physics. If you look at our solution again, if I go to Lorentzian times, it decays with sine of theta over, so the decay is e to the minus sine theta delta real time. And that is this equation. So even when I take infinite temperature, it still has a finite decay rate, which is certainly a peculiar feature. So finally, I want to ask how this translates into gravitational description, which also I'm quite puzzled about. But I think this is the resolution. So in some sense, or in any sense, having a smooth horizon implies that this naive temperature is the actual temperature. Because the Riddler-Hamiltonian generates boost, and okay, if you compute a partition function, it's traced into the minus beta h. So there seems to be a fundamental tension with having a smooth horizon. And well, in dilaton gravity, we know how to get a non-smooth horizon where you can insert a defect. So this actually seems to work, but it works in a funny way. That is, I think, both suggestive and confusing. Namely, what I need to do is I need to insert a defect with an energy-dependent opening angle. Let's see very quickly how that works. So, in the classical thermodynamics of JT gravity, of Q JT gravity with a defect looks like this. So I keep the same energy, but I've changed the entropy to be something proportional to gamma. When gamma is 2 pi, this is just an ordinary area formula. However, as you see also from this equation, gamma and theta are conjugate variables. So I can't impose this directly, I can just insert this guy here, that wouldn't be a correct answer. Instead I have to impose it, someone does the operator equation. And technically the way you do that is by having a wave function by putting a wave function on the defect and integrating over the defect angle. And then I can basically solve for this wave function by solving a differential equation. I wrote it here in terms of theta variables, but I can also write it in terms of gamma variables, again because they're canonical conjugate to each other. And then, the cell point of this integral will give me the quote-unquote right thermodynamics. One thing to note here is that this 2 pi minus 4 theta is not an accident. It's the same guy as here. It's the same 2 pi minus 4 theta that you have here, was naively you would get 2 pi. Okay, so that seems to be the answer. But it leaves many open questions. One being, does this also work in the exact quantum theory? So, unfortunately, as far as I know, defects in general dilaton gravities, we don't understand as well quantum mechanically. Perhaps if you combine some piece of literature, you can work it out. I've not given it the amount of thought that I should have, but it's something to be understood. One comment I want to make in that regard is the observation that the exact entropy for double scale SYK you can find by solving a differential equation that again imposes that gamma is 2 pi minus 4 theta. So this psi of theta is a quite complicated function. In fact, it's a Jacobi theta function. The Jacobi theta functions are famously have recursion relations. And one of them, you can rewrite the recursion relation as this identity, as this operator identity. Again, if you gamma, it's going to conjugate to theta. Trivially, this is solved when gamma equals 2 pi minus 4 theta. So that, there's this, I think there's very strong evidence that the quantum mechanical picture of inserting a quote-unquote energy-dependent defect is the way to go. However, first of all, I want the derivation of this, but I think more importantly, I don't understand what it means, or why it's natural from a gravity point of view. I'm being told by those scale SYK that I need to do something like this, but why? Why would I ever do that in gravity? What's the lesson that is to be learned here? So I don't know, obviously. Hopefully one of you can answer it, or maybe I can. One comment is that when people have talked about the sitter, the role of the observer has been very important to understand why the naive temperature is different from the sitter temperature, if you want. The SYK observer seems to measure somewhat similar physics. And so I'm thinking maybe there's some sort of similar logic that can explain this defect. In particular, the correlation between the defect and theta. Like they're somewhat conjugate, but nevertheless, if you think about it, you can think of both as like an angle of some sorts, and I'm roughly saying that the angles have to be the same, which is maybe somewhat like saying, I don't know, it smells to me similar as this energy constraint that people talk about in the sitter. It needs to be made more precise. It's somewhat more precise if you think about the DS3 gravity formulation of this sine dilaton gravity, which I haven't talked about, but there is. there, both to a defect, and if you want the boundary energy, you can associate there's a very strict sense in which you can associate an energy to a defect. Namely, defect has a conformal dimension, and also the ADM energy is associated with a certain conformal dimension, so you can map from the defect to the conformal dimension to energy, and then it's a fact that if you want the energy of the defect is the same as the energy at the boundary. So I don't know precisely what this means, but I think it means something. So that's one thing I would like very much to answer. And then the final thing is, where is the holographic screen? Which I said a little bit about, but not enough. Maybe one thing I want to say about that to confuse you all is that you want to take a look back at these correlation functions. The classical answers I found from them in q-Schwarzian. Now, these answers are quite obvious if you think of the CFT, the 2D CFT formulation of the bulk theory as two coupled Liouville gravities. Namely because, classically they are like one of the Liouville fields, and it's known that, the classical solution of Liouville theory is ADS2, so this makes a lot of sense. But it's very confusing from the Dalton gravity point of view, because you think I'm computing a boundary two-point function, and in some semi-classical approximation, a boundary two-point function should be computing like e to the minus delta times length, or e to the minus mass times length, the mass being the mass of the bulk particle. This doesn't seem to be the case. So I think this equation, it doesn't seem to be the length between boundary points. In fact, the Liouville case is already very confusing, because it has UV divergence when tau goes to 0, the correlator. But actually, the length between any 2 points in the metric that I wrote up for the Liouville gravity is finite. So I have no idea how to get something like this. Also, why do they look like ADS2 correlators if I don't have an ADS2 metric? I know. Maybe these are just not the right. Maybe these are just non-natural operators to consider in Dalton gravity. And in fact, Herman and Vladimir have proposed a somewhat new combination of operators that seem to be somewhat closer to having a gravitational picture, so maybe one needs to look at that. But I think it's important to understand this because if you compute correlation functions on the boundary and they match some sort of bulk calculation, then they're also going to tell you where the particles were inserted, aka where the boundary is. And that would give me much, it would make me much more confident, would give me much more confidence in claiming where the holographic screen lives in this theory. And once you know that, you can be much more precise about saying whether it's really capturing part of the Sitter space or not. Like which piece of the geometry are we actually describing? Okay, and I'll just leave you with this thing which I said I would say many times, so this is the last time. Thank you for your attention.
Questions for Andreas?
Can you go back to the part where you talk about needing to decrease the period in order to get the transverse action?
Yeah.
I'm thinking back to the recent with Henry Lin, where they talked about like the fake period. In that situation, they needed to increase the period by a little bit, but in this situation, you're decreasing it. Like, is there a heuristic reason to see why these two things are separate?
Yeah, I can explain that. In fact, let me also say something more after that. So their picture is as follows. This large disk is beta naive. And then what they say is, if I compute correlators, I I have only access to like a subset of this region. Well, maybe I apologize to the authors if I'm saying wrong things. But I believe this is what they say. So they only have access to this smaller region. And this smaller region is has total beta. So I'm saying decrease because I'm starting from beta naive. And I want to go to beta. They start with beta and they want an explanation of why this thing looks like an ADS2 correlator, so they want to get to beta naive,
I see.
if you want. And then they say I can insert my operators, like a 2-point function as function of tau, I can compute it, let's say here, and it's just a particle going to ADS2. Okay, so obviously it looks like ADS2 correlator. But the most extreme thing I can do is I can put them here because I don't have access to this region. Now what happens there is, if you go back to the equation, that's the reason why this guy doesn't have UV divergence. So tau is 0, for them it's like this. So it doesn't have UV divergence because in their picture they're literally not the same point. So what I wanted to add about the comparison is that in this picture, the near horizon region here is this, in the sense that let me shift things a bit, and let me consider like a portion of this disk. The whole disk is beta. This section is beta naive. And now I can say I literally cut out this region, and I identified this and this. Okay, when I do that, I get this picture. Namely, I have a defect, and the deficit angle is what I put it to be. Yeah, so there seems to be a clear relation. But I think what is there's several things that are very confusing to me. One is okay. It's how can a holographic theory live only on part of the thing? I don't know if I'm the biggest subscriber to that. So maybe that's why I'm trying to go for a picture like this with a defect. The second thing is this is only the near horizon. It's only SL2R in the near horizon region. In their case, they get it because they take like a small Q limit, but they do take some limits of the algebra, but there's different limits you can take, and if you take certain limits, I think it's like zooming in on near horizon, roughly speaking. Like you keep some of the interesting features, but not everything. And so here we have more. We have like near horizon, ADS2 with the deficit, and then some other stuff, which definitely is there if you look at the thermodynamics of double scale SYK. But then it's also confusing why the correlators look like ADS2 correlators, because I don't think it's true if you put a correlator. Even in general, like we take like the 40 black holes that Luca and Franz discussed, if I put correlators on the asymptotic boundary, the real asymptotic boundary, they will not look like asymptotic ADS2 correlators, even though the physics is governed by the Schwarzian and the ADS2 regime. The thing you probe, it knows that you put the probes on the asymptotic boundary. Yeah, so that is a confusion. The lack of UV divergence is very much confusing in a picture like this. So yeah, a lot of things not understood, but that is what I understand about the relation with what they were saying. Thank you.
Okay, so in the regime where this gives you a Liouville gravity, dilaton gravity, so I imagine then that the parameter Q will be related to like the central charge of the Liouville CFT?
Yes.
Okay. And so can you actually use this? Can you use the fact that we know Liouville CFT is exactly solved CFT to reproduce a solution of DSSYK? Like, can you map, like the Liouville physics to DSSYK?
So I should say that I think Herman and friends are working on something like that.
Who's not Herman?
Yeah, certainly Herman and Vladimir, other people involved that I should have got the name of, but didn't. But yes, you can. So you can map the sign dilaton gravity to two Liouville theories with complex conjugates and no charges.
Yeah.
So C1 is 13 plus I alpha, whatever you want, and C2 is 13 minus L alpha, and alpha depends on Q. And you can use a bootstrap, etc., and try to reproduce the results of double scale SYK. Not super obvious as far as I understand how to reproduce a partition function. I think it would be likely that it includes some sort of, you would have to include some sort of defect in the Liouville description, because if it has to be done in the dilaton gravity description. In fact, I think that's a very good way to study it, because, as you say, the Liouville theory is solved, but defects in generalized dilaton gravity are not. But if I can compute defect correlators in Liouville CFT. So maybe I can just take those results and take that as like the quantum definition and show that it works.
Okay, so what would the defect be in CFT? Some brain? Or some easy brain?
No, well, yes and no. So the setup is Liouville on a disk. But you can think of it as like that. We can think of fixed energy boundary. But then it would be literally a bulk vertex operator. So, which is also why I wrote it as V.
Ah, okay.
And as you know, yeah, this was a probably shady comment, but these guys have conformal dimensions.
Which is the opening angle then of the defect.
Yes. These energies, the energy of the boundary you can view as like set by a Verlinde loop or something, or as like a label, FCT brain label.
Yeah.
So that also has a conformal dimension, and the conformal dimensions of the two are the same. That was the comment I was making.
So you basically have, okay, then you can describe the defects as correlation functions with FCT brain boundaries.
Yes.
Okay. And those are solved by the DSSYK formula.
Yeah, those are known. Indeed. Should be some S matrix elements. Because the 1 point function with FCT boundary condition is the S matrix element of the category or whatever you want to call it.
Any other questions? If not, let's thank Andreas again.